In the world of computer science, there are some algorithms that are just special. Not just useful, but truly beautiful. Today, we're going to talk about one that might just take the cake, the fast Fourier transform. Is it the most ingenious algorithm ever? Well, let's find out.
Okay, so think about it like this. Most algorithms kind of live in two separate worlds. In one world, you've got the workhorses, right? These are your graph searches, your sorting algorithms, the stuff that makes our digital world actually work. They're essential, but maybe not always breathtaking. And then, in this other world, you've got the purely beautiful algorithms. The classic example is Towers of Hanoi. It's this gorgeous, elegant recursion. It's inspiring to study for sure, but you're not exactly going to build a company on it.
But every now and then, you find something that breaks the mold, an algorithm that is both, and that's the fast Fourier transform, or FST for short. This thing is an absolute gem. It's the engine behind so much of our modern life. We're talking Wi-Fi, image compression, GPS, you name it. But at its core, it's also one of the most stunningly elegant pieces of logic you could ever imagine. So, how are we going to unpack this beast? Well, we could dive deep into signal processing, but that gets messy. Instead, we're going to discover the magic of the FFT by tackling a problem that probably gives you flashbacks to high school algebra: multiplying polynomials. Yep, that's right. And our whole journey starts with one simple question: is there a faster way to do it? All right, so the way we all learn to write down a polynomial is pretty straightforward, right? It's just a list of its coefficients. For something like 3x squared plus 2x plus 1, you just think of it as the numbers 1, 2, 3. It's the standard way. It's how our brains are wired to see it. But, and this is a big but, here's the problem. When you multiply two polynomials this way, let's say they're both degree d, you end up multiplying every single term from the first one by every single term from the second. That leads to a runtime of OD squared. Now, if d is small, who cares? But what if your polynomials have thousands or even millions of terms? Suddenly, OD squared isn't just slow, it's a deal breaker. It's the villain of our story. So that's the big question, isn't it? Can we actually do better? Is there some clever trick, some secret path that lets us blow past this O for D squared speed limit? Well, the answer is yes, but it requires a complete change in perspective. And this leads us to the first of four brilliant ideas. What if the bottleneck isn't the multiplication? What if the real problem is how we're writing the polynomial down in the first place? Think about this. You only need 2 points to define a unique line, right? It's a fundamental rule of geometry. Well, it turns out that idea scales up perfectly. You can define any unique degree d polynomial just by knowing d plus 1 points that are on its curve. So, instead of a list of coefficients, what if we represented our polynomial by a set of points? This is a totally different way of looking at it, and it's called the value representation. And why would we do this crazy thing? Because look at what happens to our multiplication problem. If you have two polynomials in this value view, and they're evaluated at the same x points, multiplying them becomes laughably easy. You just multiply their y values together, one by one. Our runtime goes from that horrible OD squared all the way down to a beautiful linear O of D. It's an absolutely massive speed up, all from just changing how we look at the problem. Okay, so here's the new game plan. It's a 3-step process. Step 1. We take our polynomials in their normal coefficient form and convert them to this new value form. That's called evaluation. Step 2, we do that super fast pointwise multiplication. Easy. Step 3, we take the result, which is in value form, and we have to convert it back to a regular polynomial with coefficients. That's called interpolation. So it seems like we've solved one problem but created 2 new ones. Great. Let's just tackle that first puzzle, the evaluation step. Because if it takes us OD squared time to evaluate our polynomial at all those points, then this whole grand plan was for nothing. We're right back where we started, stuck in the mud. So we have to find a fast way to get from coefficients to values. And this is where brilliant idea number 2 comes in. It's a classic computer science move: divide and conquer. What we're going to do is take our polynomial and just split it in half. We'll create one new, smaller polynomial with just the even-powered terms and another one with just the odd-powered terms. Now, why do this? Well, the math works out beautifully. You can see here that the original polynomial, p of x, can be rebuilt using these 2 smaller even and odd parts. But look closely at the formula. Both the even and odd parts depend on x squared, and that's the key. It means if we pick our evaluation points cleverly, like, say, +2 and -2, then x squared is just 4 for both of them. We can do one calculation and reuse it for two different points. Bam, we just cut our work in half.
This seems amazing, right? We can just keep doing this recursively and solve the whole thing. But there's a huge fatal flaw. This whole trick hinges on using those plus/minus pairs. But to go one level deeper in the recursion, we need to evaluate our new, smaller polynomials at the squares of our original points. So if we started with +2 and -2, the next level needs to use 4. And, well, that's it, just 4. Our plus/minus pairs completely vanish. The symmetry is gone. The recursion is broken.
So we're stuck. Or are we? This is where the story takes a wild turn. This is brilliant idea number 3. To save our beautiful recursion, we have to do something radical. We have to leave the comfort of the real number line and step into the world of complex numbers. And we're not just going to use any complex numbers. We need a very special magical set of points called the nth roots of unity. What are they? They're simply all the complex numbers that solve this equation, x to the power of n equals 1. If you plot them, they look incredible. They're just n points perfectly spaced out on a circle. So why these specific points? Because they have two properties that are, for our purposes, pure magic. First, just like we wanted, they always come in plus/minus pairs. Perfect. But second, and this is the part that should give you goosebumps, when you take the n roots of unity and square all of them, you get back the n/2 roots of unity. Think about that. The exact structure we need to keep our recursion going is perfectly preserved, all the way down. It just works. And just like that, we've solved the evaluation puzzle. That whole recursive process we just built, that is the fast Fourier transform. But we're not done. Remember our grand plan? We still have to do step 3, interpolation. We have to get from our point value representation back to the regular coefficients. And honestly, this feels like it should be an even harder problem to solve. But now, let's look at the math from a different angle. If we write out the FFT as a matrix operation, we see something stunning. On the left here is the matrix that does the forward FFT. On the right, the one that does the inverse. Just look at them. They're practically the same matrix. The only real difference is that for the inverse, you use the inverse of omega, our root of unity, and you have to scale by 1/n. And this leads to the fourth and final brilliant idea, which is really more of an astonishing discovery. Because these matrices are so similar, you don't need to write a whole new, complicated algorithm for the inverse. You can use the exact same algorithm you just wrote for the forward FFT. The only thing you change is you swap omega for its inverse. That's it. It's like a one-line code change to solve a problem that seemed impossible. I'm going to borrow a quote from the lecture this explainer is based on because it's perfect. So if your mind isn't blown, you haven't been paying attention. I mean, seriously, the idea that the solution to this really hard reverse problem was just hiding in plain sight inside the forward algorithm the whole time, it's absolutely breathtaking. So let's just walk through that incredible chain of logic one more time. First, the brilliant idea to change representations to make multiplication fast. Second, the classic divide and conquer trick of splitting the polynomial into even and odd parts. Third, the leap of genius to use complex roots of unity to save the recursion. And fourth, the unbelievable realization that the inverse algorithm is the same algorithm. It's this beautiful cascade where each idea builds perfectly on the last. Look, the story of the FFT is about more than just a fast way to multiply polynomials. It's a powerful lesson in creative problem solving. It shows us that sometimes the best answer comes from completely changing your perspective, from finding a hidden structure that no one else saw. And it really makes you wonder, doesn't it? What other elegant, beautiful shortcuts like this are still out there hiding in plain sight, just waiting for someone to find them and solve the next generation of impossible problems?